voice will record, right? Yeah, record, right? Yeah. Okay. Very good afternoon to all of you. It's 4 o'clock again. I try my best to make you not sleep. Right. So till now I've been actually slightly gone technically inside about these microsensors. So the first kind of sensors we discussed was a biomedical sensor, where you found that there was a reaction between a few chemicals, and then there was an increase in number of charge carriers that give rise to increase in current. So the increase in current is proportional to the glucose level. That's what we saw last class. So next one I'm going to talk about is a biosensor. A biosensor is a kind where we are going to have some sensors. There's some sort of a base sensor, but there is a sensing medium will be used here, which is a biomolecule. Okay. When I say biomolecule, it could be, so one day, the other day, I think some student answered, it's an enzyme. Enzymes are one which, that's a lot of help for us. Or proteins. Okay. So these biomolecules are used as a sensing medium to detect anything. Okay. So the detecting measurement could be another biomolecule itself, or it could be a chemical or something like that. So the example here, instead of measuring, we call the sample which is to be detected as analyte. And if you see here, the BB, what is written is for the biomolecules. Now the sensor could be of different types. One common sensor that is used for biosensing, I will now explain. We call this as conductometric sensors. Okay. Now imagine that we manufacture in a PCB. Okay, the normal PCB, you are actually making circuits, right? So imagine we make a copper lines. These copper lines of about, say, it's around 0.5 millimeters, and the gap between these two, say, it is around 2 millimeters. Okay, say we have several of them. So what do you come out about this now? This is, if I now connect a multimeter between these two, and I can measure the resistance, what do you see? What will be the resistance between these 2 points? Huh? Infinite. I mean, the impedance is so high, or it's like 2 wires which are disconnected. Can you see that? Can you realize that? Yeah? Yes, so this is on a PCB. Okay? Now what I do is, say suppose I add a drop of water here, or I add something here. So what will happen now? Now again I'm still measuring the resistance. What will happen?
Very low.
There is a resistance, or you will see a value of resistance here. Yes? So the reason for this resistance is because of what? Of water which was added on the top of this. Yeah? Do you agree that? Yes? So these kind of sensors, which we call it as interdigitated electrodes. We call it as interdigitated electrodes. We call it, and usually maybe using many manufacturing techniques can be adopted. The simplest one is a simple PCB fabrication. Okay. Now what in biosensors they do, say for example they take this kind of a conductometric sensor and they coat those sensing material, which I said the biomolecule on the top of this. And what happens is, after coating this biomolecule, you will find a new resistance value, right? Yes? Now then they can, for example, if they coated some kind of an enzyme. Now enzymes are biomolecules which will have some kind of activity towards certain chemicals or certain compounds. Okay. Now what will happen is the activity of this enzyme can reduce or decrease because of some specific samples. One example I want to show in the next slide is a group of researchers. They have developed such a system where they could find out that they wanted to find out how much pesticide has been mixed in water in a storage tank, what people drink. Okay, so they used enzyme. They could see that in this picture they used one with the, there were two sensors were used, similar what I discussed, and probably one was the sample which they want to test, and one was as a reference. Okay, so what they found is if there was any difference in between these two resistance, that was actually measured through some measurement system. Okay, just I want to ask some questions. Can you identify anything which probably you must be knowing a generator? Why do you think there is a generator here? What could be the meaning of this?
How are the sensors?
Okay, let's go little basics. Now I said that there is going to be change in the resistance, or you will say there is a change in the impedance. Okay, right? Now, when there is a change in impedance, how can I measure it? One is I can measure through multimeter. Now what happens when I now connect this to a multimeter, and if I connect this to resistance mode, when I measure this, I will be seeing the resistance is keep on increasing or decreasing. Why do you think it may be happening so? This is because it's not just a resistance change, it's actually an impedance change. There could be some capacitance also could be changing there. Because there are two electrodes and there is a capacitance is also forming there. Yeah? So to measure this change in resistance, change in impedance, probably one can think of a circuit. Something like a signal generator is there, and probably the sensor which is actually having some change in impedance can be connected, so there is a load resistance. Using a simple potential divider circuit, I can now measure what is the change of this. Yeah? Why do you think I should connect a signal generator, an AC signal?
Because you can set it at 0 phases.
No. Why do I need an AC signal? Because there could be a capacitance as well. There is a total thing is an impedance change. So probably we may not be able to use directly DC. If you use DC, you will see that the voltage what I'm measuring across that load resistance will be always increasing. So one may need to have this kind of a signal generator. I'm just draw a simple circuit how we can measure this the change in resistance. Okay, so that's an example of biosensors. Okay, chemical sensors. Hope this next few minutes will be very interesting for all our activities. Chemical sensors. Let me start with, say for example, I have an ion chain. So what happens is I keep this ion chain in this room, and then I come back after 5 days. Okay, what I will see? A mild brownish layer. Okay, the iron slightly started rusting. I come after 10 years of time. What will happen? Yeah, the rusting level, there could be more rust. Yeah, the rusting level might have increased. Okay, can anyone this side explain how rusting happens? Chlorine ions. Okay. Water, oxygen. Yeah. Okay. Anybody else? This side. Can you explain how iron gets rusted? Probably everybody is having the answers, but we are not saying. Yeah. Very good. Oxidation. Yeah. So what happens is the oxidation. There is an oxygen molecules here. The oxygen is slowly reacting with this iron, and it's actually rusting the iron. I mean, the iron is ferrum, Fe. It's becoming ferric oxide. The oxygen is getting higher. So if you ask a chemical engineer will say there's an oxidation reaction. It's actually the oxygen level is increasing. So the amount of oxidation has occurred. From that, I will read how much oxygen concentration was there. Yeah. If you ask a mechanical engineer, he will say the rusting was, there was an increase in rusting. The mechanical properties such as density or Young's modulus, these properties got changed. Yeah, so density, there's an addition of mass. Yeah, he will say the density has increased. If you ask an electrical engineer, what he will say? Electrical or mechatronic engineer?
Conductance.
Conductance. Correct. Because of this addition of rust, the resistance got changed. The electrical engineer should say the resistance has got changed now. The electrical properties have got changed. So the amount of rusting will actually going to affect these impedance values. And that is proportional to the amount of concentration of oxygen has reacted to it. Yes or no? Yeah? So what this simple example tells us that if you want to detect a chemical or a gas, for example, in this case was an oxygen, we want a material that has to react with it and change its properties. The easiest one, what we being electrical engineer, we will look for a change in electrical properties such as resistance or capacitance, or mostly resistance is more easier. Okay, so different engineers can explain this in different way, like what I mentioned, but the idea here is what I said. So another point to look into is, but the reaction is very long time. Yeah, it takes so much of time to detect the oxygen there. We don't want that so much slow sensors. If there is any gas leakage inside some, say, an aircraft, we want immediately an alarm system, not after 10 years. It will lead to fatal things. So the sensor should be very fast and responsive. So the sensing medium should be responsive, and the sensor which is doing the job of detecting that change of the resistance or mechanical change also should be quick enough, right? So we can classify these kind of chemical sensors into 4 groups. Since my research also is which going to be towards this, I may be going more detailed. Right, so 4 chemi-resistors, chemi-capacitors, chemi-mechanical, and metal oxide. These are the 4 kinds of sensors. Don't worry, there are a lot of chemical formulas coming. Don't think that you are in a chemistry class. We are in electrical class only, but we are seeing in a different angle. Yeah. So let me start with so as the name says, chemi-resistor is basically there could be some chemically sensitive. It could be a polymer. When I say polymer, let's clarify then and there. Polymer is like plastics. What we have, plastic covers. They are polymers. Yeah, something like that. Yes, which are mostly made up of carbon, oxygen, and hydrogen. We say polymers. Yes. So maybe something like that, or some metals. When they react with the specific measured gases, they can change in resistance. We say is chemi-resistor, or change in capacitance, we say chemi-capacitors. And chemi-mechanical is, as I said, the mechanical properties can change for presence of gas. Okay, I'll come to that 4 little later. So I want to go for an example which actually covers the point number 4, the 4th type and the 1st type. I'm going to go a little detail of this. So before I go to make everyone to be on the same level of little chemistry, then and there I have to check out. Anybody who can say what is SnO2? Very good, tin oxide. Who said that? Great.
Should they eat dioxide?
Huh? Tin oxide. Sorry, these days I'm not.
So it should be dioxide.
ZnO. Zinc oxide. Very good. TiO2. All are awesome. Should get Nobel Prize. WO3. Yeah? O3. No. Huh? Tungsten? Very good. Tungsten oxide. It's not tungsten trioxide, it's tungsten oxide. Very good, very good.
It's 3 oxygen.
In2O3. Engineering oxide. Yeah? Indium oxide. Very good. Very good. So, the common thing, what you see in all these things, what you see, the common thing in all these materials? Oxide. Okay? So, metals, when they, metals, some of the metals can readily, quickly get oxidized. Even aluminium or copper, they can quickly get oxidized. Okay? And in particular, these materials, tin oxide or zinc oxide or titanium dioxide or tungsten dioxide or indium oxide, they are very much used for sensing gases. Okay? Just because when you zoom and see there how they look like under a microscope. Say I have a sheet of this material, and then I go to my SEM laboratory there, and I zoom and see inside that, you will see structures of this. At the outside you will see like a single filling, yeah? But when you zoom and see at the range of 10 micrometers size, actually we see some crystalline, or there are grains of structures of that material. Either they are fully attached or they are very close to each other. But overall, as I said, they are there as a filling. Do you get this point? What I am trying to say? So, you can see that between one grain to another grain, there is a gap. Okay? Right. So, let's proceed. So, either the grains, they adhere partially or they stay just nearby. So, when I say that they are going to partially adhere or attach, as an electrical engineer, what do you think could be happening here? First of all, a metal is a pure conductor. But when now we are going to oxidize it, it's not going to be that pure conductive. Yeah? It's going to have some resistance now. Now I said these grains are not fully attached, they are just adhering partially. So what do you comment now on this? Yeah, so no, the capacity, that means now there is some impedance has been creating, because if say I am connecting this to a voltage source, okay, the current flow will not be that beautiful, because there is a small barrier between one grain to another grain. The electrons may need to suffer to jump, yeah, from one grain to another grain to have a flow. Yes, yeah. So what do we call this? There is a what is it? The conduction band is a bit far away. Yeah. So let's just keep this in mind and let's go to the next. So much of chemistry. Don't get scared. Don't get scared. I'll teach you. So what happens here is, I'm going to talk with respect to this top figure. Okay? Closely observe me. It's very easy if you observe now me. So what I'm doing is, I'm zooming this earlier picture what I showed you, which had the grains. I told you they have, when you oxidize, the metals form these grains. Okay? This is quite normal chemistry. But we don't worry about the chemistry, what is happening here. We will see how we can make this as a sensor. Now I'm just going to zoom only two closely attached grains. Now what happens is, since they have oxygen, that means they all have oxygen at the end, right? So what oxygen does, the oxygen traps the electrons. And they trap the electrons, and so the electrons cannot move from one grain to another grain. Do you get this? The oxygen traps the electrons not to move from one grain to another grain. So that means more the oxygen, more the electrons cannot move, so the resistance will be higher. So if the oxygen content is more, the resistance is going to be higher, because I'm going to have this barrier a lot and the electrons cannot move. When we will generate current, when the electrons move, yeah? When the electrons cannot move, we don't have the current, or there is no conductivity. Yes? So what happens is, but these materials, say suppose now I have a, okay, again we go to the basic chemistry classes in your school. You know this oxidation reaction? You said very nicely. There is a opposite reaction for this. What is that? Wow, man. Okay, great. Reduction reaction. So what happens in the reduction reaction? Yes, very good. So when reducing reagents, like for example, when more reaction of hydrogen, the hydrogen and oxygen can combine and the oxygen can be removed basically. So in a reducing reaction, for example, reducing gases like carbon monoxide, okay. So when these gases react with these metal oxides, now what happens is these oxygens are removed, okay. The oxygens are removed. So when you remove the oxygen, now there is an ample amount of electrons can flow. Do you understand? So I said that when the oxygens are more, the depletion layer is more. Now you remove the oxygen, the depletion layer is getting reduced. You should be able to understand what is depletion layer when I say with connecting to your transistor circuits. Yeah, we have the conductivity in a transistor also depends on the depletion layer.
Yeah, in the FET classes you might have listened. So same thing. So when I remove this oxygen, but because of the reaction of the reduction gases such as carbon monoxide, I will produce electrons. So these electrons can flow from one grain to another grain. That means the conductivity increased. So this conductivity increase is proportional to the concentration of the gas in presence of what gas it was. Okay? So there are some simple formulas where one can actually relate this concentration. Okay? So the same is applicable if you are now having a gas, if you pass more oxygen, the resistance will more increase. Do you understand? So either you pass a reducing gas, you can also measure, or you have a more oxidation gas, that also you can detect. Okay? So the principle here, what we need to identify is, these materials give us the change in resistance which the electrical engineers need. Yeah. So chemi-mechanical sensor types. So in the chemi-resistors, it's a matter of, don't worry, I won't talk too much chemistry. As I told you, the chemistry knowledge, what you have is what I have also. You're all same here. Right. The example of chemi-mechanical sensors. So before I go to this topic, I want to start with the example. I think I mentioned this before also. Again, certain metals, for example, in this case, palladium. Palladium is a quite expensive material. So when palladium is exposed to hydrogen, what happens is the hydrogen molecules are very favorable to it. They go and sit there and they form palladium hydride. This is something like I have a sponge, I dip it in the water molecules just stay, and the sponge, what happens to the sponge? Expands. The sponge expands. What happens to the mass of the sponge? Increases. So how much amount of water the sponge can accommodate is how much amount of water it absorbs. Yeah, right? So in this case also, this palladium, it has been observed that, so this actually is not the result. Somebody has already found that when there is a 3% of hydrogen, they found that there is a change in the mechanical properties. So the mechanical properties, okay, before that, mechatronics might have already heard. So let's talk about the electrical engineers here. Okay, mechanical properties. Can you give some name of mechanical properties? Whatever you know.
Yield strength.
Yield strength.
Proof stress.
Okay. The very basic things in structural mechanics, three main properties one has to know to decide what material property it is. First one is the density. So density defines the mass of a material. Okay. Next one is the Young's modulus. Young's modulus is a constant of a material. So I apply for this material, if I apply a stress, it's going to bend. Or if I try to pull this with certain force, it's going to extend. Or in other words, there will be a strain to this. So this ratio of stress by strain is a constant for all material, and that's Young's modulus. Yeah. And next one is the Poisson ratio. We don't go into too much detail. So these are some constants of a material. Okay. Now what happens is, what here they say in chemi-mechanical sensors, on reaction of some chemicals, these materials will change their mechanical properties. On absorption of gases, for example, in this case, they say that the Young's modulus decreases by 14%, or density decreases by 2%, or volume increases by 10%, because it's absorbing hydrogen. So what people have done in chemi-mechanical sensors. Yes, please. So they constructed cantilever beam. Cantilever beam is very simplest structure. Yeah. I told you last class itself. Cantilever beams we come across a lot in many engineering structures. One end is fixed. So I told you every object in this world will have its fundamental frequency. Yes. Did I tell you last class? Okay. So what happens is, when I coat this palladium on this, on a cantilever, say it's made up of a silicon microstructure, and this is a palladium film. Now, the fundamental frequency of this structure, say it is some X hertz. Now, upon absorption of gas, the mass is changing. So, once mass changes, the resonant frequency of this structure will change. So, the amount of gas which was absorbed is proportional to the resonant frequency change of that structure. So, the mechanical engineers will see this as a change of these material properties, but we being electrical engineers will measure the resonant frequency of this. Any idea how can we measure this? It's a little extreme question I ask, but let's see, anybody can say this. Huh? Our question is, I just now said these mechanical properties are changing. The mechanical engineers are very happy. Okay, these materials are changing. Okay, that's what it happens. They will stop. But we cannot stop that. We have to build a circuit. So if this is the case, how can we build a circuit, or how electrical engineers can measure this change? Somebody said very nice. Yes. Strain gauges. Yes.
Piezoelectric.
Okay. Piezoelectric. Okay. Okay, there are many ways to do. One way what people do is, they shine, okay, since you are very happy with optical communication and optics, you're very happy. You're not happy with that? Happy. So what happens is, when the hydrogen sits on this, that means, I said there is a mass, increase in mass. It's something like, the beam was like this. Once I sit on that, it bends. When the hydrogen sits, the beam bends. Okay? So when I shine laser light on this, from the reflection of this laser light, how much it deviates, people can measure. Okay? Through optical circuits. The other possibilities is, probably one has to connect some resonator circuit, which I don't want to confuse you. Already I can see some people are angry with too much of chemistry what I'm talking here, but actually I'm not talking that much. So just to summarize before I go to the next topic, I was started saying about these chemical sensors. I was saying there are 4 types, and I said a very, very important principle behind it. I'm just telling the fundamentals. So I said how chemi-resistor sensors, what is the principle behind that? I just reviewed it, and then I said how even there is another way is chemi-mechanical, where mechanical property changes, and using that how we can develop sensors. Okay, so the metal oxide sensors are very the same what I said. Actually, I combined the first and fourth together. Yeah? Okay. Now comes Rama's topic. The next type of, so first I saw biomedical, I said then biosensors. Now I'm going to the acoustic wave type sensors. How many of you are getting distracted with that picture? Okay. Don't sleep, huh? Okay. Right. So, what I'm discussing now is I'm discussing the principles of sensors that are used in these MEMS devices. Okay. The next type of principle what I'm going to discuss is use of acoustic waves. Now, when I say acoustic waves, this is sound waves. Okay. Now, what I'm talking now in this class or how you hear. Anybody can explain that? How we hear. When I talk, how you can hear. What happens?
Vibration.
Vibrations. What happens is, when I speak, the air molecules are vibrating in the air medium, and then it reaches your ears. The vibrations are passing through, something like what you see in this fellow. The first pendulum is strike, yeah, and you see the last pendulum is getting actuated. The particle movement is actually transferred from one pendulum to the next pendulum, and it reaches there. Yeah, same thing. The vibrations from me is actually translating from this point and reaches to all of you there. Now, this is an air medium, but if I do the same thing, say in this table, if I strike this table, again I'm producing a sound. It actually reached to some extent and it died off. Same thing happened. The particles in each of this wood, it vibrated for a moment and it transferred, it died off. So these vibrations, when they are traveling on, this kind of sound waves, when they travel on elastic medium, we call it as acoustic waves. Now what is this elastic medium? Anything, any material medium that can actually expand and contract. That means I take a structure, I stretch this, okay? Once I release this stretch, it should come back to its original position. We say it's an elastic medium, yeah? But I stretch in such a way that a lot and it is not turning back, it's also okay, but that means you cross the limit of the stretch what you can apply. You cross the elasticity limit, okay? So, any medium that can, so in such mediums, when the vibrations travel on that, we say it is acoustic waves. Now these acoustic waves, sometimes they can travel only on the surface, just on the surface it can travel, or sometimes it can travel on the bulk of this material. Now what is bulk means? Bulk sounds like a really bulk. Yeah, correct. Say for example, I take the same this eraser here. If the waves travel only on the surface, we call as surface waves. But if some waves also can travel inside that, there are some vibrations can travel in the inside of these. The waves we call it as bulk waves that travels all along the body of the structure. Okay, so accordingly, a big broad clarification we can give as surface and bulk acoustic waves. So these have been used as one of the very principal mode of physics that has been, for building the both sensors and as well as actuators. Okay, right. So I classified now the acoustic waves into two terms based on the way whether it is traveling on the surface or inside the medium. Okay. Now the classifications can be still given a little more. How the waves are traveling. Now, as I said, the way how we talk. So I was talking, and the waves are traveling towards this direction. I don't see my voice traveling backside to me. Yeah, correct. Yeah, the waves are traveling towards this side. So that means the particles are vibrating parallel to the source or parallel to the wave direction. This we call it as longitudinal waves. Okay. The second type is, it is transverse waves, where the waves are traveling in a wavy nature. Probably you can read that discussion what I mentioned. It's something like I have taken a blanket and I'm just sweeping it. I produce a wave. What you can see is, just note down this red color dot here. It just goes up and down. So these are the two kind of wave models which are possible in elastic medium. But what is used in sensors? Okay, or an example is in a football match, probably there is a Mexican wave. It's actually a typical transverse shear mode waves. So many waves I'm going to show today. Now, when these two longitudinal and transverse mode combine, we call it as Rayleigh waves. Okay, too much of physics, huh? Too much of chemistry first, now too much of physics now. Not that much. I'm just. So in a Rayleigh wave, so the best example of Rayleigh waves, when earthquake occurs, the wave that happens on the surface of the earth crust is actually a Rayleigh wave. Or you drop a stone in a water, the ripples that forms is actually a Rayleigh wave. Now the combination of when a surface medium is going to have both the transverse and longitudinal. So when I strike something, and if both occurs on the surface, then we call it as a Rayleigh wave. The interesting thing, what you can notice, there is a yellow circle actually is moving in a elliptical path. So this is typical characteristic of a Rayleigh wave. So the fellow who found this actually got a Nobel Prize already and this became a very important type of acoustic wave for designing sensors. So just a single nutshell, I want to revise this what I was saying. I was saying that I was talking about elastic medium. I introduced something called as acoustic waves, and I classified into two big groups, surface and bulk. And then also I said there are further more types based on the way how the mode propagates. It's longitudinal or transverse, and when they two combine, we call it as another name, which is called Rayleigh. There are some more waves. If it is this, all of your head will fall down, and then you will say that give me PhD tomorrow. So I'm not going to continue about that. So let's keep these things in our mind. Now all these waves you must be imagining, probably when I say the blanket example or ripples in the water, you can imagine in a macro level. But now we have to concentrate ourselves and come to a micro level. It's all in a tiny chip, say in 1 millimeter of size. We see these waves, and these waves are used to make sensors. Let's see how. So, one of the important kind of, which actually we will come across many times, very well known sensor type is a surface acoustic wave, which is actually which uses these kind of acoustic waves to sense quite a lot of measurements. Okay. Now, how these waves can be produced in a material? So, in our case, when I want to make a sensor, I want something where I can apply electric voltage, and I want to receive electric voltage only. I don't want to see how these waves are moving. I'm not interested. I'm an electrical engineer. I don't want to know what the hell the waves are going on. I want to see only what is the change in current or voltage or frequency or phase or amplitude. These are my things I want to know. Yeah. Okay. So to do this, there are certain materials called as piezoelectric materials. Have you heard of piezoelectric materials before? Yep. Mechatronics metal here. Anybody else except Claudia? Anybody have heard what is piezoelectric materials? Okay. There are, yes, good. Oh, okay. So, there are certain materials which actually on application of force, it can generate potentials, generate voltage, or if you apply voltage, it will vibrate. Okay. So, probably as how I gave a small introduction to the acoustic waves, before I say the sensor principle, I slightly go into the piezoelectric effect very quickly. A bit of. So what happens in these piezoelectric materials? Only certain type of materials, because of their molecular arrangement, the charges of those materials always behave neutral. For example, say a piezoelectric material, in this case, say there is a charge of the material, something like this. So these are some atoms. So I'm taking an example of a quartz, which is commonly called as quartz, which is silicon dioxide. So these are some oxygen molecules, which are negative, electron rich, and these are silicon molecules. Sorry, silicon atoms. So all these things form a molecule, a single molecule. Now what happens is, when you press this, you tend to move. Okay, when I try to press from the top, okay, what I do is I move more of this. If I try to move this side, I try to move more of the positive charges towards this direction. I think I'm making some mistake. Sorry, let's see the picture there. Forget this, what I'm drawing here. Okay. What I'm trying to say is, so this is actually a typical atomic structure of silicon dioxide. So what happens is, when you don't apply any stress here, they actually form neutral. That is, both the positive and negative charges are balanced. But when I'm going to, say for example, compress this, the number of positive ions increases towards one direction, and the number of negative ions are increases in the other direction. That means one surface is going to be more positive charge, and one surface is going to be more negative charge. That is, we have now we have created this charge imbalance. So when we connect two wires across these two ends, one can actually generate potential. This is what is happening. Okay, so same thing can happen when we are going to stress this. So either you increase the negative charges in one side, or increase the positive charges on one side. So that's why when we apply a force, we actually generate charges. Okay, right. So this is the same principle when we actually have a cigarette lighter. There's a small piezoelectric element. When you try to press this, there are some charges introduced there, and that actually creates a spark. And there is a pump where the petrol vapors are coming up and it burns and it actually catches fire for a while. So the intention is just we create that spark by these charges. Yeah. So what I'm trying to say is when you press these materials, the charges which were neutralized, okay, it is something like, say for example, I'm a positive charge guy and there are two negative charges here. Okay. When you press together, what happens is, say I'm going more inside this medium and the two negative charges are coming towards this direction. So when you take a mean average of this, there are more negative charges this side and there are more positive charges this side. So when you connect this outside, you actually collect these charges as electricity. Yeah? Now same thing happens when you apply electric potential. Instead of now pressing this, moving this charger, now we move the charges, we are introducing more negative charges on one side, more positive charges on the other side, the crystal expands. So either you apply an electric potential or you apply force, you get this actuation in the crystal. Now this is so fascinating by nature. The amount of electricity what you apply is exactly proportional to the structure what is changes. So if you vibrate in a particular frequency, the signals what you say also is exactly that frequency. That's why this has been extremely well used as crystal oscillator in all our circuits. If you see your Altera boards, you see that 50 megahertz, 50 megahertz is the crystal. Yeah, that's actually a quartz crystal there inside. Okay, so that quartz crystal was cut in such a way that that resonant frequency, the mechanical resonant frequency was 50 megahertz. So when you apply, so it vibrates at that 50 megahertz, it shakes at 50 megahertz. That means every 20 millisecond it's shaking, is it? So it's producing that sinusoidal signal for us and it is running our microprocessors. Okay, so that's actually the earlier when you apply force and when you get charges, we call it as piezoelectricity. The inverse is actually inverse piezoelectric effect. So when we have such mediums, we have such crystal, now you understand that when I apply pressure, I'm moving these charges. Okay, when I apply pressure, I'm creating strain. Basically, when I apply pressure, there is a strain, and I'm now relocating this negative and positive charges in the substrate. Okay, but at the same time, when I apply electric potential, I'm actually introducing more charges in there and trying to expand the crystal. Now, if that is the case, what they do in how to make us a sensor, keeping all this physics, what I refreshed now on the waves, and as well as on the piezoelectric effect, people devise microsensors by making interdigital electrodes. Previously, at the beginning of the class, I actually introduced interdigital electrodes for biosensors. I showed you cone structures. They were disconnected metals. That is on a PCB I said. Now what I'm saying is, we make such cone structures. You can see that there is a formula I have given here. Lambda equal to 2 into d, where d is the distance between probably one center of this distance. Probably you can observe that yourself. So one can actually, so when I'm going to have this kind of an arrangement, now what I do is I connect this to a signal generator. So when I connect to a signal generator, I have a sinusoidal wave. So at one instant we have positive, another instance I have negative, positive, negative, alternating voltage. So what happens when the first cycle of signal is applied to this, say that this is coated on a piezoelectric substrate. So this electrode will have positive charge. Am I right? This will have a negative charge. So what will happen? I am going to make one, whenever the positive charge is, probably there could be a vibration or a deformation like this. Maybe where the negative was there, the deformation could be like this. Can you imagine this? So an alternative deformation is happening on the surface. A mechanical deformation is happening. Can you imagine that? Yeah? So as more and more we push the alternating current here, these mechanical waves will start traveling on the surface. The strain is actually traveling on the surface. The strain is just traveling. It's exactly like how what I said about the acoustic waves in the very beginning, that guy who is seeing the pendulum there, the first pendulum was striped up So the last pendulum is moving. How it was moving? Because the second is pushing, the third is pushing, fourth, and so on. Same thing here. These IDTs, when I apply electric potential, there is a deformation. Actually, these are particle movements. These particle movements will push the adjacent particle, the next will push the other one, and so on, and there will be a waves on the surface. Yeah. Now, this is exactly the same way how the waves are traveling in the air, but it's happening at the surface. Now, what people do is they make two such interdigital electrodes on the same substrate. One they connect as an input, one other as an output. So now you can readily imagine that when I apply the electric voltage here, I produce the strain here, and these strains are traveling as vibrations on the surface, and it will reach the other end. So when it reaches the other end, it's again the inverse piezoelectric effect, where the vibrations that has reached this electrode will generate voltage now. Correct? So here I apply voltage, electrical signal. I generate a mechanical energy. This mechanical energy reaches this IDT, and the mechanical energy is converted again to electrical energy. Yeah. So basically, what I will see is the signal what I apply here, I should see again here. Yeah. Correct? Yes or no? Whatever electrical signal I apply there, I should see at the output. But only thing what is happening in between these two is the signal transition is not happening because of a wire. It's happening because of a mechanical wave. Yeah? Yes or no? So what people have done is this velocity of the waves which is traveling on this is actually fixed. For example, sound velocity in air is about 330 meters per second. Sound velocity in wood could be different. Sound velocity in water could be different. Different medium will have different velocity of wave. Can you say why? Because the particles, how much they can move inside this depends on that particular density, Young's modulus, and so on. So when we coat something in between these two, okay, a sensing medium, when we coat in between these two surfaces, this sensing medium can actually, well, what happens is when either it absorbs certain gases or certain molecules, it will actually going to affect the velocity of the waves because you have something extra on the top. Yep. This is something like two guys are running in a beach shore. Okay. So one guy suppose I'm running. I'm jogging on a road. Okay. If you're jogging, I do not. The single pack will not be there. That's a different case. So I'm running on a road. Okay. With the shoes and I'm running there. Next day, what happening is I'm actually running in a particular velocity. Next day, what happening is I'm going to carry some bag. I'm going to carry some also something I got from Speed, and some market items I'm going to have in my hand and I'm going to run. Do you think I can run in the same velocity? No, because I have some mass in my bag and hand. There's an increase in mass. Yeah. So obviously my velocity will not be the same like how I was when I was free. Yeah. So same thing happens here. So the waves which are traveling when there was nothing on the surface between these two, it will run at a normal acoustic velocity. But when we coat something there and that coating is now attracting something extra, that is going to change this velocity. So this change in velocity we can see as a change in electrical signal in terms of change in frequency or in terms of change in amplitude, or it could be in terms of change in phase. Okay? So a typical example I'll just touch here. So I have actually whatever I said I have explained here. So I will stop with this example, too much today. So a while ago I was telling you about the mechanical sensors. I told you that there is a film. Here I was saying that I have a palladium film. This film can absorb hydrogen and it expands, or there is an increase in mass of this film. Did I say this? Now say that we coat this palladium film in between these two transducers. Say we coat that in between these two transducers, something like this. A short picture is here. So what they say is the blue color one, what you see, the blue color of the signal, what you see is the electrical signal that was collected at the output IDT when there was no hydrogen. But you see when there was a 3% of hydrogen, the red color signal, you can see that it has got little shifted. That means there is a change in phase of this electric signal, which is actually caused because of the addition of mass of hydrogen atoms or molecules in the palladium film. So the amount of shift that has happened here is proportional to the concentration of those measured. Likewise, people have, researchers have developed several applications of making sensors. So in a nutshell, one more thing. I don't know whether you will kill me if I talk about this. We have one last thing I will talk and then I will stop. So what I was saying about is an example of a surface waves. People also use bulk waves. This is a very primarily used a quartz crystal. So this is like a quartz crystal. One electrode is made on the top and another electrode at the bottom. So when you apply electric potential, there is a vibration along the bulk of this material. The material in the bulk vibrates, or we say something like what is happening in the picture. So this is more established than SAW, where what happens is when suppose if there are any mass loading changes on this surface, the change in the mass is actually measured in terms of change in resonant frequency of this crystal. So when I have this crystal, if I make oscillating circuits, any examples of oscillating circuits you have studied in your second unit? Phase shift oscillator. Have you studied about oscillators? Oscillators. Yeah, crystal oscillators. Have you? Okay, then probably I should not talk much about this. Or probably all of you are very dry. Okay, quickly I will recollect what I was trying to say overall. I actually showcase you different kinds of microsensors and their principles. So these principles, if you see, they follow some physics or chemistry fundamentals that is actually used to make it as an electronic device. Okay, so next part of the section we will see one temperature sensor. So temperature sensor, any idea? You might have already used. Any idea what physics is behind that? Mechatronics students? Yeah? Have you heard of this Seebeck effect? No, not seeing back effect. Seebeck effect. Okay, thermocouple.
Yeah.
Two dissimilar materials. Okay, when they are tied together and they are maintained in two different temperature, maintained in a different at the temperature condition, you will actually see a voltage generating at the other two ends. Yeah, thermocouples. Okay. The same principle is also used in microsensors. I will quickly see this on Monday. And another important sensor is a pressure sensor, where we'll go a little detail about that. So overall, I was just going through some of the principles behind this. Probably I won't go much of chemistry. I can see some faces changing there when I talk about some material sciences. Let's see how much I can reduce that in the next lecture. But that's it for today. Okay. Right. It actually differs.